Hi everyone. So the goal of this video is to look at the kinematic equations. So this is a should-do assignment. The reason why I think this is important is because the kinematic equations can be used to describe the motion of any object if you just know a few things about that object's motion. Alright, so your learning target is to implement the correct kinematic equation to describe the motion of an object. And so when I say correct one, you're going to have a few choices, and you need to think about what information are you given and which equation should you use. So let's look at these equations. All right, don't get overwhelmed, or maybe feel overwhelmed. I don't know, I can't tell you how to feel. But you can try to understand what these variables mean if you just break down each one at a time, or like what each equation means if you break it down. So we might know that this is final velocity, this is initial velocity, this is acceleration, this is time, or the change in time. We could also see change in position, or what we call displacement. And all these equations have the same variables, just in different arrangements. Now, these equations have been derived from other equations, and I won't go into all the detail there, but basically what makes these useful is that each one has about 4 variables. And if you know 3 of them, you could find out the other one. The other thing, why there's 4 of them, is that each one has a situation where you don't need to know one of the variables. So for example, number 1 here, you don't need to know displacement to use this equation. For the second one, you don't need to know acceleration to use this equation. For the third one, you don't need to know final velocity. And for the fourth one, you don't need to know time. And so I think that's why all these equations are useful, is that even if you're missing a piece of information, you can still figure out what you're trying to find. So let's look at a few examples, and let's try to use the correct kinematic equation. All right, so a common rule in driving is to stay 2 seconds behind the car in front of you. Imagine you're driving on the highway at 60 miles per hour, which is about 26.8 meters per second, and the car in front of you starts to stop. It takes you 0.5 seconds to react, and then you slam on the brakes for 1.5 seconds. Assuming your final velocity is 0, how far do you go while you are braking? So I think this is an interesting question. I think especially as young people, you might have heard this rule, as a common rule that you might be taught when you are learning how to drive. So let's think about, what does this mean, and like, can we figure out how far this person goes when they are slamming on the brakes? So it says, how far do you go while you're braking? So this is the one that we're trying to find. We're trying to find delta x. Time, we know, is 1.5 seconds. Initial velocity is 26.8. Excuse my terrible handwriting, but I'm trying to write quickly because I don't want to take 20 minutes to make a video. Final velocity is 0, and we don't know acceleration. So I'm just going to put an x there because I don't know what it is. But I don't need to know, because if I look at the equations over here, there's an equation that will help me figure out my displacement. And I think it's equation number 2. Equation number 2 has displacement, it has final velocity, initial velocity, and time. So if I plugged all my numbers into this equation, then I'd be able to get my answer. So real quick, delta x, maybe I'll just set up the problem. Again, I don't want to bore you with all the math, unless I really have to show something crucial here. What, 26.8. Again, if you're watching this video, it probably means that you've been able to move through some of the other problems about acceleration pretty quickly. Probably means you've got some pretty good math skills. So I'm not going to bore you with all this stuff. But we just set up our problem, and then you can kind of figure out what to do mathematically. All right, so this would be our mathematical setup. If I'm using this equation, it's final plus initial divided by 2, and then times time, or our change in time. So I would end up with 26.8 divided by 2, that's 13.4. 13.4 times 1.5, that's going to be somewhere around 20. So my displacement would be 20 meters, or somewhere around there. If you want to do the math, you can check my answer. But that's about, I don't know, 65 feet, 70 feet. So imagine slamming on the brakes and sliding for 70 feet. And if you aren't careful, then you will hit the car that is right in front of you that has decided to brake. So that's why, especially when you're on a highway driving at 60 miles per hour, you want to make sure you keep your distance from the car in front of you. Because even if you slam on the brakes, your car might take some time to come to a stop. And your car might slide, and you might slide a pretty good distance. You might slide right into the car in front of you. So not only is this a physics problem, but some real world advice. All right, let's move on to the next one. Okay, a track runner is at the starting line of a race. In the first 2 seconds, they accelerate at 8 meters per second squared. How far does a track runner go in the first 2 seconds? All right, so as a person who's very interested in athletics, I was kind of curious to know, how does physics relate to athletics? I know for a fact that this is something that Olympians will look at. They'll look closely at their start off the line and see how well are they accelerating, how long does it take them to reach their top speed, and then they might do some drills based on whether or not they are good or not of their acceleration. And you really try to break down all the little things that make you good at running just a 100-meter dash. You want to look at all these little segments of your run. Anyways, let's break down what we got. So let's look at the information that we were given. Let's see, we know they accelerate at 8 meters per second. So I'm at 8 down here. Let's see, we don't know their final velocity. Initial velocity, we're going to assume it's 0. This is a tricky one, but if you're starting a race, you're not moving. And then displacement is what we're trying to find, times 2 seconds. Okay, so all that considered, we need to find an equation that's, let's see, actually we don't need final velocity. Let me put an x there because that's not what we're really looking for. We're looking for displacement. So we want an equation that has displacement, but also has initial velocity, time, and acceleration. And I think that's number 3. All right, so real quick, if I wanted to set this up, I'd go displacement equals, and I'll try to be real quick so I don't want to bore you, 0 for my initial velocity times time. That will go away. That's always kind of a nice feature about some of the equations where if your initial velocity is 0, it might make the math a little bit easier. All right, and then we have a 1/2 times a times delta. Oh wait, a is 8. So let's make this look like an 8. There you go. Beautiful. All right, 8 times t squared. 2 squared. All right. That's an ugly 8. I wish I could make it prettier, but you guys know what I meant. So we have 0 times 2. That becomes 0. We have 1/2 times 8. That becomes 4. And then 2 squared becomes 4. So all of this becomes 16. So you have displacement is 16 meters. So in the first 2 seconds of a race, this person has gone 16 meters. And that, doesn't seem bad. They still have another 84 meters to go if they're running a 100-meter dash. But again, this is something that an athlete might look at to see what can I do to make sure that my first 2 seconds I'm getting off the block really well, and I set myself up for a good position to win the race. The other thing I'll point out real quick, for some of you calculus people, this might look familiar. A 1/2 next to a squared. I think you might have to think about integrals and derivatives, but just a connection between physics and calculus. I won't bore you guys with that though. Okay, let's move on to the next one. All right, during takeoff, a 737 plane has to accelerate to a velocity of 160 miles per hour. That's about 71.5 meters per second. The runway is 2,000 meters long. What acceleration does the plane need for a successful takeoff? So I know some of you might have done some internships at some places nearby. Pratt & Whitney, there's a few other places that, pretty much build plane engines. So this is something that is directly related to that job. You need to make sure that you have an engine that can produce enough power and get the plane to accelerate so that it can actually take off before it runs out of runway. So, these are things that people consider and make sure that their machines do what they want them to do. All right, so let's kind of go over what we have. We have displacement. We know that we need 2,000. 2,000 is our axiomat, like our maximum number, but we'll put it in now. And if we were able to make a more powerful engine, then maybe we wouldn't need the whole 2,000 meters. Time, we don't know. It's not given to us, and that's not what we're trying to find. Initial velocity will be 0. Let's imagine that a plane's taking off and it's not moving, which is kind of what most planes do. Final velocity is 71.5. And our acceleration is what we're trying to find. All right, so again, you might have noticed this pattern where there's always one variable we don't know. There's another variable that we're trying to find, and then we have 3 of the other numbers. Okay, so let's look at the equations that we have. We need something that has final velocity, initial velocity, and displacement, and acceleration. Acceleration is what we're going to try to find. Well, if you look carefully, maybe you can pause the video and try to figure it out. But I'll tell you the answer. It is number 4. And so you've noticed that we've used 3 out of the 4 equations. I didn't use the first one because it's kind of easy to use. I think you guys can kind of figure that out. Honestly, it's just a rearrangement of our acceleration equation, right? Acceleration is final velocity minus initial velocity divided by time. If you rearrange that, you could get an equation that looks like this. So that one's kind of straightforward. This one, we got squares and all kinds of fun stuff over here. Let's make sure we understand how to solve this one. So we have, if I plug in my numbers, I have 71.5 squared. Can't tell you how many students forget about the squared. And that's going to be, oh wait. Let's just mess it up. We need an equal sign here. We have 0 squared, which just becomes 0. We don't have to worry about that later on. Again, nice little feature of initial velocity being 0. And then we have 2a times 2,000. Okay, I'll try to fill this in really quick. Okay, so when you are doing this math here, if you're ever trying to find final velocity, make sure you remember that it's final velocity squared. So that's going to be important. But this is the general setup. I think you can do this in a calculator. You're going to get some huge number. And then on this side of the equal sign, you're going to have 4,000 times a. All right, so you have 4,000 times a equals some huge number. And then, again, I won't bore you with the math, but after that, you're going to have to divide both sides by 4,000. And then you'll be able to get what a is, and that's your final answer. So hopefully this was useful. Again, I don't want to bore you too much with the video and too much math and all that, but I wanted to show you 3 of the equations, 3 of them that can be the most complicated. Notice that for this last one, we tried to find this variable that's kind of tucked into the equation, but you can do a little bit of algebra to find any variable in any of the equations. In this case, we just needed to divide, we got to this point where we needed to divide both sides by 4,000 in this case. But for any of these variables, you might have to do a little bit of algebra to find the one that you are looking for. But again, that's usually just maybe a little bit of multiplication, addition, trying to cancel things out on both sides of the equal sign. If you need help with that, glad to help. All right, but those are the kinematic equations. Again, I think they're really cool. I hope I gave you some examples that you think are interesting, and there might be a few practice problems that you can try to kind of play around with some of this stuff. All right, good luck.